Assalamualaikum and have a good day everyone. Hopefully you are doing great today. We are still in chapter 6, stability. Listed are the learning outcomes that should be achieved by the students at the end of this chapter, as mentioned in the last week lecture. Basically, in this chapter, you are expected to be able to generate and interpret the basic root table in order to determine the stability of the closed loop system. So for this week lecture, I will cover part 2 of chapter 6. Remember, in the last week lecture, we were introduced three conditions of stability for control systems such as stable, unstable, and marginally stable. We will also learn how to generate and interpret a basic root table in order to determine the stability of a system. For this week lecture, we will consider two special cases that can arise when generating the root table. Without further ado, let's begin our part 2 of chapter 6. Basically, there are two special cases that can occur when generating the root table. The root table sometimes will have a 0 only in the first column of a row, or the root table sometimes will have an entire row that consists of 0. Let us examine the first case, which is the case when the root table sometimes have a 0 in the first column of a row. If the first element of a row is 0, division by 0 will be required to form the next row. To avoid this phenomenon, an epsilon is assigned to replace 0 in the first column. The value epsilon is then allowed to approach 0 from either the positive or negative side. Let us look at an example. Determine the stability of the closed loop transfer function below. Table 6.4 shows the initial layout of root table for example 2. Table 6.4 is formed by using the denominator of the transfer function. I hope you still remember how to create this root table. Remember, you can start with labeling the row with power of s, from highest power of the denominator of the closed loop transfer function to s power of 0. From the denominator of the closed loop transfer function, we can see that the highest power of the denominator of the transfer function is s power of 5. Therefore, the first row of the first column must be started with s power of 5. After that, you can start filling the table with the coefficient. The coefficient with highest power of s in the denominator must be put first, followed by other coefficient. From the denominator, the coefficient for the highest power of s, which is s power of 5, is 1. Therefore, the second column of the first row must be started with 1. And please always ensure to rearrange the coefficient as shown in the table. We are now ready to complete the table 6.4. However, as seen in the table, a 0 appears in the first column, which is in the s power of 3 row. So, what should we do now? In order to form the next row, which is s power of 2, a division by 0 is required. As stated in slide number 6, this phenomenon can be avoided by assigning an epsilon in order to replace 0 in the first column. I repeat, this phenomenon can be avoided by assigning an epsilon in order to replace 0 in the first column. We already replaced the 0 in the s power of 3 row by epsilon. Again, what should we do now? The next step is completing the table as usual. We now have the completed root table for example 2 using epsilon value. Since the stability of the closed-loop system using Routh-Lewis criterion is determined based on first column of the root table, therefore our attention will be only on the first column of the root table. Therefore, the second and third column can just be ignored. Again, our attention will be on the first column of the root table only. Why our attention will be on the first column of the root table only? Yes, because the stability of the closed-loop system using Routh-Lewis is determined based on the first column of the root table only. Now, to begin the interpretation, we must first assume an epsilon with positive and negative sign. For simplicity, let's replace all the values of epsilon in the first column with positive 1 for positive epsilon and negative 1 for negative epsilon. Table 6.5 shows the first column of table 6.4 along with the resulting signs for choices of epsilon plus and epsilon minus. From table 6.5, we can see that there are sign changes for both epsilon plus and epsilon minus. Then, how can we interpret the stability condition of the closed-loop system based on table 6.5? If epsilon is chosen to be positive, table 6.5 will show a sign change from s power of 3 row to s power of 2 row. And there will be another sign change from s power of 2 row to s power of 1 row. Hence, the system is unstable and has two poles in the right half plane. Alternatively, we can choose a negative epsilon. If epsilon in the first column is replaced with -1, table 6.5 will show a sign change from s power of 4 to s power of 3, and there will be another sign change from s power of 3 to s power of 2 row. The results will be exactly the same as for a positive epsilon. Hence, the system is also unstable and has two poles in the right half plane. We now look at the second case, which is when the root table have an entire row of 0. Sometimes, while making a root table, we find that an entire row of 0, because there is an even polynomial that is a factor of the original polynomial. This case must be handled differently from the case of 0 only in the first column of a row. Let us look at an example that demonstrates how to construct and interpret the root table when entire row of 0 is presented. Determine the number of right half-plane poles in the closed-loop transfer function below. Therefore, in this example, you are required to determine how many poles in the right half-plane of the S-plane based on the closed-loop transfer function given. Table 6.6 is the initial layout root table for example 3. I'm sure you already know how this table is generated. Remember, our attention only on the denominator of the closed-loop transfer function system. All the values in the second row is multiplied with 1/7 for convenience. However, if you still want to retain with the original value 7, 42 and 56, there is no problem. You can still continue with that values. We stop at the third row since the entire row consists of zeros. In order to complete the root table, we need to follow the procedures. Then, what are the procedures we need to follow? The first procedure is we need to return to the row above the row of zeros. If the row of zeros is at s power of 3, then the row above the row of zeros that we are interested for is row s power of 4. Once we have the row, the next procedure is to form the auxiliary polynomial using the entries in that row as coefficient. The polynomial will start with the power of s in the label column and continue by skipping every other power of s. In this case, the polynomial will start with s power of 4, continue with s power of 2 and s power of 0. Thus, the polynomial form for this example is ps equal to s power of 4 6s power of 2 plus 8s power of 0. We now have the polynomial equation Ps equal to s power of 4 plus 6s power of 2 plus 8. The third procedure is to differentiate the polynomial with respect to s. The equation here is obtained based on differentiation of the polynomial with respect to s. The last procedure is to use the coefficient of differential equation to replace the row of zeros. The last procedure is to use the coefficient of differential equation to replace the row of 0. You may also multiply the third row with 1 over 4 for convenience. Thus, the row become 1, 3, and 0. The remainder of the table is formed in a straightforward manner by following the standard form. Table 6.6 shows that all entries in the first column are positive. Meaning that there are no sign changes occur in the first column of the root table. Hence, there are no right half plane poles. Then, how about the stability of the closed loop system? Yes, the system is considered stable since there are no sign changes occur in the first column of the root table. Let's try another example for the case when entire row is zeros. For the transfer function Ts, tell how many poles are in the right half plane, left half plane, and on imaginary axis. Table 6.7 shows the completed root table for sample form. At the s power of 3 row, we obtain a row of zeros. At the s power of 3 row, we obtain a row of zeros. Moving back to one row, meaning s power of 4, we extract the polynomial. The polynomial, let's say Ps, from s power of 4 is s power of 4 plus 3s power of 2 plus 2. Taking the derivative with respect to s to obtain the coefficient that replace the row of zeros in the s power of 3 row, we find the differential equation as for s power of 3 plus 6s plus 0. Replace the row of zeros with 4, 6, and 0. And you may also multiply the row with 1 over 2 for convenience. Finally, continue the table to s power of 0. You may use the standard procedure in order to complete the table. Then, how do we interpret the table? The results of the first column of table 6.7 are summarized as in table 6.8. From table 6.7, since all entries from the even polynomial at the s power of 4 row down to s power of 0 row are a test of the even polynomial Ps, then we can conclude that no sign changes exist from the s power of 4 row down to s power of 0. Therefore, the even column does not have right half poles. Since there are no right half pole, meaning no left half pole, are presented because of the requirement for symmetry. Hence, the polynomial Ps must have all 4 its poles on the imaginary or j omega axis. The results are summarized in the first column or even column of table 6.8. The remaining roots of the total polynomial are evaluated from s power of 8 down to s power of 4. From the first column of table 6.7, we notice that there are 2 sign changes occur from s power of 7 to s power of 6 row and from s power of 6 to s power of 5 row. Therefore, the other polynomial must have 2 roots in the right half plane. Since there are 2 right half plane poles, meaning that there are also 2 left half plane poles are presented because of the requirement for symmetry. The total column is the sum of roots from the even column and other column. Thus, system have 2 poles in the right half plane, 2 poles in the left half plane, and 4 poles on the imaginary axis. Therefore, it can be concluded that the system is unstable because of the right half pole. Okay, that's all for this week lecture. We will continue with the last part of chapter 6 next week. Take care and see you next week. Assalamualaikum.